about my dog. Um, I smell, because I cleaned up like 10 times last night, the dog. And I'm pretty sure, I know I took a shower this morning. I knew I got up clean clothes, but I think so if you see like dog something on me, or if I smell like dog something, I just smell that smell.
You're probably like parents smell like baby throw up or worse. I did manage to take a shower, but I am wearing the same thing as I wore yesterday. It's tough times. Yeah, it's mid-semester.
Um, well, good. I'm glad I'm not the only one that might smell like
Yesterday.
dog fluid or baby fluid. Play from current slide is where we're at. So I did start the video, and we're gonna make progress. And William, I'm gonna talk about the nonlinear analysis. If I don't talk about it at the very start of class, after we get back from spring break, we're going to take the rest of the day off. If I don't start the class out with at least mentioning that, we're going to take. So I'm now motivated enough that there's just no way. There's no way that we're not going to talk about it. So I just don't want to take the time because we could spend easily 10 minutes talking about it, but I'll do that when we get back from spring break. So we are here. We did this. We deleted a couple variables. I've seen a couple of you are actually running analyses as we're going through this, and so far everything looks good. I'm going to use somebody's speech notes.
Yeah, the speech part isn't good anyway.
And so far so good. So one of the questions that we have to answer is, how many components should we extract? It's an important decision that we make, and we want the principal component we want our analysis to account for as much variance as possible in a parsimonious model, right? We could account for 100% of the variance if we had as many components as we have variables, but that doesn't seem like a very reasonable solution. It certainly isn't parsimonious. And so we want to account for as much variance as possible in as parsimonious of a model as possible, or as a model with as few components as possible. That would ideally be a better solution than a model that had this greater number of components and didn't explain any more variability in your overall data set. So the most common criteria is just to include components that have eigenvalues greater than 1. And you saw in the preferences that we looked at for factor analysis that that's what SPSS defaults to, and that's what most people do. And it's probably the reason why most people do it, being a bit cynical here, is because that's just what SPSS does, and that's just sort of an easy, well, if SPSS does it, that must be the right thing to do. And but there are better ways, and we'll look at some better ways to do that. So you just think about when we talk about eigenvalues, they represent the amount of variance that's explained on one of our components. In principal components analysis, each variable has an eigenvalue of 1, therefore eigenvalues less than 1 represent less variance than a single item. And so that's some of the logic that gets used for why eigenvalues greater than 1. So that's the default. Just extract components, and by components, it's how many dimensions are there to your data? Are there 2 dimensions, 3 dimensions, 4 dimensions, 10 dimensions, 16 dimensions? How many dimensions are there to your data? So that's really what we're talking about here, which, if you sort of think about the whole reason why we're doing principal components analysis, boy, that's really an important question that we have to get a solid answer to. And as you'll find, I'm not a big fan of eigenvalues greater than 1 because it is 1 is rather arbitrary, and we'll see that soon. Another way that is oftentimes used is a scree plot. Anybody know what the word scree means? Any outdoors people here?
It's something related with a cliff.
but I can't remember what's about the cliff that is the screen, the profile of the cliff.
Sort of, yeah. Tyler?
Like the fine granular rock, or like pieces of rock. It's not super granular like gravel, but it's
Yeah,
just
it's
nightmarish to
yeah.
walk through.
I think that's how it's that. If you go to a mountainous area, go to Colorado and get below a big peak, and you'll see where rock rolls down that peak, and that rock um, is called scree, and we have what looks like a cliff here, right? And we have scree, therefore the name that gets applied to it is a scree plot. And with a scree plot, you can estimate the number of components based on the point that the curve begins to straighten out. And so what we have is on the y-axis, we're plotting eigenvalues. And remember, SPSS does eigenvalues greater than 1. And so SPSS would, is it 4? Would it extract 4 components if you draw a line from 1? Does it come to, or is it 6? Somebody can, what do you think? If you look at, if we draw a straight line across from 1, where does it come? Does it come to 4? 5? 5,
yeah.
Okay. Everybody's looking like this. How about if you look, you have it in front of you?
It looks
Huh?
like directly above 5. It is like directly.
Yeah, and we can actually look at the actual eigenvalues in just a minute. But if we use that criteria, eigenvalues greater than 1, I'd say gives us 6 components. I don't even look at my own notes. Eigenvalues greater than 1 gives us 6 components. So 6 must just barely be above 1. We'll look at it in a minute. And so that would be, we could do eigenvalues greater than 1, or we could use the scree plot. And the scree plot, we look for where the line first begins to straighten out. Can somebody tell me visually where that line first begins to straighten out? 3. Not 9, or how about 14?
Oh, yeah.
It looks like it's straightening out down there.
13, between 13 and 14.
Between 13 and 14, yeah. We could actually do some. We could get really fancy and look at sort of the angle that it changes. I don't know if I had to pick where the elbow was in the thing.
Oh.
It seemed, where was the elbow?
So like
3
7.
maybe?
3.
I don't know.
That's what I was thinking.
Did you say 3?
I didn't think.
I think, but it does seem sort of arbitrary, right? It seems a bit, you might say 3, I might say 14, right? And so it doesn't seem nearly scientific enough to me. And so that's the second way, less common than eigenvalue greater than 1, but the second most common way to determine the number of components. I find that to be probably equally troubling to use. I guess maybe one sort of consideration here would be, remember this is exploratory. If you pick 6 and I pick 8, that's just different ways of exploring the data, and there's probably something to be said there. But my preference, and what I'll want you to do, is to use a different way to determine the number. You can look at those 2 ways, but we're going to look at a different way to determine the number of components to extract. And I give you some people that are more expert than me, or at least they have a citation that you can use for why eigenvalue is greater than 1 and 1 is problematic, why this scree plot is potentially problematic, and give you a citation for that. And what we're going to do is an analysis called parallel analysis. And just think about this, and SPS does all of this work for us in 15 seconds. And so what it does is we give it we give the parallel analysis a couple inputs, and it takes and uses a random number generator, or it's a pseudo-random number generator that SPSS has built into it. And it generates a set of data that's the same dimension as our data. Same number of cases, so the same height, and the same number of variables, the same width. But it's just random data. It's just garbage. It's just noise. And then we perform principal components analysis on that, and we extract the eigenvalues for those principal components analysis. And then we repeat. And we can repeat it 100 times or 1,000 times or 10,000 times. Once you get above 1,000, things don't change much. But I think I probably would do 10,000 because it's just so easy to generate 10, and it takes just a few seconds. It'll generate 10,000 random sets of data. Each set of data, it will calculate the eigenvalues. And then it will record your eigenvalues and give you what the mean eigenvalue is for all 10,000 or 100 or 1,000. And then it will give you the eigenvalue at the 95th percentile. And then you can use that to compare to your data. Because remember, this is just junk data, right? This is just randomly generated data that happens to be the same dimension as your data. Run an analysis on it. Calculate the eigenvalues. If your data is no better than what junk data can get, it doesn't seem reasonable to extract that component. And so that's the preferred way of determining the number of components to extract with your data, with your principal components analysis. So I'm going to show you how to do this, and I'll post to Canvas. It's a small bit of syntax that you'll use in the analysis. And essentially what we'll have is we are going to give it 2 inputs. I think by default, principal components analysis is selected, so we don't have to worry about that. But we just need to tell it how many cases, how tall is our data, and then the number of variables, how wide is our data. And we just need to fill in, and you'll see when you open up the syntax file that it will look just like this. It'll be question mark, question mark, question mark, question mark, looking for your input. And you just fill in a number here, fill in a number there, tell it to run, and then it's going to give you some output. But I'll show you, we'll just do that quickly so you have that. So I'm going to go to SPSS. I'm going to say File, Open, more specifically syntax. And then you're going to point to the syntax file that you're going to download from Canvas. That's called parallel.sps. And you're going to open that up. And you really don't have to, if you care about syntax, you can read this and you'll probably get some idea what it's doing. But all we need to do is fill in these 2 inputs right here. I have this set at 10,000, and if you want to do 1,000, that's fine. If you want to do 100,000, that's fine. 1,000 is plenty, but I'm going to leave it at 10,000. And how many variables did I start out with? Anybody remember? 17. So I'm going to I would have gone through and I've deleted some variables because of low MSA values, but I'm just going to do this with my original data. 17 and, anybody remember the end? 344? 344. And so n is equal to 344, and make sure there's a period behind that. And then this is 1 is principal components analysis, and then 2 would be factor analysis. And so just make sure that there's a set to 1.
Are they backwards? Yeah,
Oh, thank you. So 344 and 17, good catch. Number of variables is 17, right? 17 variables wide, 344 cases high. And then I can never remember if you need to highlight, but I always just highlight all of the syntax and press the play button. And you can see where it says it's running down here, and it will run for just a minute or less. And it's done. And then it comes up with this output for us. And this is the output that we'll look at. And this is the mean for those 10,000 data sets. This is the mean eigenvalue for the first component. And this is the eigenvalue at the 95th percentile. And as you change, if you decided you were going to do 100,000, it would just take a few more minutes to run. But these values will almost not move at all. Even though, because even with random data, there's a point where some stability is reached. And so you're going to do this analysis with your data using your inputs, of course, not the inputs that I just used here. And then we're going to actually look and interpret that output when we get to the right slide. So we have analysis that looks like this. And again, here I have 320 and 15 because I deleted a few variables. And we care most about the 95th percentile. And so that's the column that we're going to be looking at. And so here is this is I don't know if it's the most important, but it's probably one of the first really critical tables that SPSS gives us. It's the total variance explained table, and we can see that that for the first component, the eigenvalue is 3.004. For the second component, is 3.720. Here's the sixth. Remember, we were debating on whether it was 5 or 6. The sixth component was 1.01. And this is the default in SPSS. So it extracted, if you look at this part over here, where it says extraction, it extracted, it only filled in the data for the components that it extracted, and it extracted all components that had eigenvalues greater than 1. So it stopped here because 0.889, of course, is less than 1. So if we go back and look at the previous slide, so remember 3.004 for our first component. We're going to go back here, look at the first component, look at the 95th percentile column. Is our data better than this data? Remember, this is just the randomly generated data, and at the 95th percentile, the eigenvalue is 1.47. Is ours greater than that? Because it was 3.004. So we have confidence that our data is greater than you'd expect to get by chance, because that random data is just chance data, because it's just randomly generated data. So for the first component, we have some confidence because ours is 3. The junk data had 1.4, right? 1.47. Mm-hmm. And so we feel good about that. Now we're going to look at our second component, 1.72. And the junk data had 1.36. Do we keep it or not? Are we comfortable with? Is it greater, good, or bad?
Slightly good.
Huh?
Slightly better?
Slightly better, but good enough, right? Because we want our data to be greater than because this is the second component. We want our data to be greater than the junk data. This is just the randomly generated data.
That's
Junk. Random. Yeah. Noise. And our data said we're at 1.72, right? For the second component. And when we look at the second component for the data that we generated, it's 1.36, and we're higher than that. So we should have some confidence that we're beyond the 95th percentile. So the first two components seem to be reasonable components to extract. How many people don't understand that process, how we came to that conclusion? Everybody tell everybody to yourself, look at the third component. What is it? 1.276? And don't shout it out loud, but make the determination of what we do with it from looking at this. And you get 15 seconds, and then a quiz. So what number did we have?
So we're gonna get rid of it.
1.276.
What did we have?
Jump data is 1.279.
1.276?
Six
So it's a difference of
and 1.279.
So it's a difference
Ours
of
is just
So it's
slightly
lower.
worse than the jump data, so you would.
I think I could live with three 1,000s, right?
Yeah, 0.003
I would
difference.
just because.
Doesn't,
Because ours is slightly lower, or slightly higher.
it's slightly lower.
Lower. Yeah, I would keep it. That's just being too much. It's being too rigid. If you think that it's below, but how about the next one? How about the fourth component? What is it?
1.146.
1.146. And sorry, I can't work the thing here. And what do we have for the fourth here?
A lot below.
1.219.
That's considerably less, right?
Less by 0.1-ish.
Yeah, and so yeah, I find it sort of, I'd find it difficult to sort of add that fourth component because it is far enough below the 95th percentile. In fact, it's below the mean, isn't it? What was it? 1.2 what? 4? Yeah, and the mean was 1.23, so it's below the mean value. So conceptually, maybe it's just because it's 10 after 5 on a Wednesday. Does everybody follow what we're doing? Does it not just follow, not just have steps in your head, but understand why we're making the decisions that we're making?
So it's with like significance, like I guess significance level of like by chance. So we're saying by 95% confidence that it's a factor.
Right, and that's why we're using the 95th percentile.
And point which would be like 0.05.
Yep.
And so then once we got to the third one, which is like one where it's below, does that mean we stop looking or do we go to the next one?
There's no way that if you're the fourth one or the fifth one will be even worse.
Be even
It's-
worse.
Yeah,
Okay.
it's
So we
it
don't
won't
need
get
to
better.
go through every single one.
That's right.
As soon as the first no-go, we don't have to keep going.
Right.
Okay.
And so in our case, how many components using the parallel analysis would we extract?
2.
I think we got 3.
Or 3.
Because unless you wanted to sort of draw the line firmly at less than, but it was so close. So with the parallel analysis, we get 3 components. Eigenvalues greater than 1, we had 6. The scree plot, I don't know what I said, 3 maybe. Brittany had 14. No, somebody else. So yeah, so we had, but not a lot of agreement, right? Not a lot of agreement for sure. And so this to me is just a much more. It's just a better way instead of the arbitrary 1. Because look at with the junk data, we have all kinds of components that are the eigenvalue is greater than 1, and remember it's just a random number generator that came up with the data, and it just doesn't seem like I'd want to hang my sort of ability to do research on something that just by chance would also
So would you get different if you ran that again? Would it give you different numbers?
slightly.
Slightly?
And the larger, like I did 10,000, so if I run it again, it's just going to be slightly different, maybe to the thousandths. If you only did 10, it's going to be vastly different, because if you have 10, you can easily move 10. But when your n is equal to 10,000, you'd have to have some really strange eigenvalues to start moving those very much. So it's because, yeah, they would be slightly different. In our case, maybe just to the thousandths. Certainly wouldn't change. Maybe with that third one, it might either be a little bit more closely yes, or it might just fall a little further outside of the yes, but we probably would still say it's close enough because it's within, 5 or 6 or maybe a few more thousandths. So parallel analysis makes sense.
I wanted to ask, so we're still like in the framework of like we went through checking the diagonal, deleting things, rerunning it. Then we moved to
Yeah.
the next one, checked it, eliminated what we needed to, rerun. So then we like go to this step,
Yes.
check things,
Yeah.
rerun it. So how, if we've already been deleting things like as we're going, because I know like this example, did you already delete things?
I deleted, from this case I deleted 2 because I said it was 17.
Okay, I guess what I'm just thinking is like, if
Yeah.
we've been doing that each step and rerunning it each step, so getting all the way down here, do you still see like as many problems? Or should they
Yeah,
have
because
already been eliminated?
these problems are different than the problem that we were trying to eliminate by deleting variables. And we're going to get to that problem in just a minute. This is a slightly different challenge than that challenge. So everybody okay with parallel analysis?
Are we deleting anything from this analysis?
Are we what?
Are we deleting anything?
No, but we're going to make a change and rerun our analysis. And the change we're going to make is we're going to not use the default eigenvalues greater than 1. We're going to tell SPSS to extract exactly 3 components, because that's what the parallel analysis tells us to do. And so we're going to, and that's, remember I told you that remember this screen, because we're going to come back to this screen. So what we're going to do is we're going to do our factor analysis, and then we're going to say extraction. And instead of based on eigenvalues, we're going to say fixed number of factors, and we're just going to say 3 because that's what the parallel analysis told us. If your parallel analysis told you 6, you're going to do 6. If it tells you 2, you can do 2. And in some cases, that's going to be exactly the same, because maybe all of yours, all of the eigenvalues are greater than 1, and that's what the parallel analysis tells you as well. So in some cases, you may not have to come in here and make any changes, or even rerun it, because all of yours were greater than, all of your eigenvalues were greater than the eigenvalues for the randomly generated data. And until you got to below 1. And so we just need to, this would be, in my case, I would just make this change and I'd rerun the analysis, and instead of giving me 6 components like it was, it's going to give me 3 components. Make sense?
So it's, how I see it is that the eigenvalue, or however you say it, is not as superior as doing the parallel analysis.
Just using eigenvalues greater than 1 is not as it's not as accurate, and it's somewhat arbitrary.
Okay.
If somebody said 1 is a nice round number, let's just use it.
Just like 0.05.
What's that?
Like
Just like 0.05, yeah. And so the parallel analysis at least has a little bit of weight behind it in terms of the empirical assessment of comparing your eigenvalues. Really, you're doing a statistical test, right? Is that eigenvalue statistically significant or not? And we're doing that by comparing it to the 95th percentile. And if yours is greater than the 95th percentile, you can say that it's significant at p is less than 0.05.
And sorry for
You're good.
questions. So the cases, n cases refers to the number of participants,
That's right.
And then
list-wise.
list-wise, and then the number of items, the variables. Is that what the?
That's right. The number of variables in your analysis
And
at that
so
point.
I kind of was missing with the end data sets because you said you can use 1,000 or 10,000. So how do we determine that with our data set?
Pick a number, either pick 1,000 or 10,000 or 100,000. It's just how many randomly generated sets of data is it going to compute for you? Yes, and it does. It's just it's speaking of arbitrary. It's an arbitrary number.
But the minimum is 1,000.
I would say 1,000 is a minimum, and for 10,000, I just like 10,000, and you might want to do 500,000. But again, it probably won't change once you get above 1,000. Things become really stable, and 1,000 probably would get you no different results than 10,000 or 100,000 or a billion.
I was just going to ask if it's important for it to be above, my end, because I have 3,000, my data set's 3,000, so 1,000, but I need to do 10,000.
No, it would be, you could still do, the size of your data set, the height of your data set, that is the number of participants, wouldn't be a consideration that you'd make when you're determining how many sets of randomly generated data to produce.
So that after we change it from eigenvalues greater than 1 to whatever number we've come up with
Yep.
in parallel analysis, from an output perspective, do we see the results in the confidence matrix? So you would have had initially 6, now you have just 3 confidence?
Right. And so we would see, and I don't think I ran it, I think I just changed it and I canceled it, but if I run this again and it's at 3 and say, okay, I must have ran it, we can see if we look at the components, now it only extracted 3 components, right? Before there were 6 components that it extracted here, and now it just extracted 3. Because we don't think that this 4th one is meaningful because it's below what we'd get if we just took a set of data that is similar to ours, that just result.
Something we would write up in our manuscript.
You would write up that you decided to extract 3 components using parallel analysis with a 95% confidence. Yeah. Other questions?
Is there any point that we should look at the items, right, that are loading onto these factors and make a decision that way? I'm seeing that these are coalescing around this concept. So rather than, I think the parallel analysis and the eigenvalues, all of this is important. But if I notice these questions are coalescing around a concept, or at least I think they are, how much does that factor into this decision?
For me, that would be the next step. And so after we determine how many components we should extract, then we would do that assessment to see to what degree are things coalescing. And you may see that they're coalescing, and you may see that there might be coalescing around 4 components or 5 components. But if the parallel analysis indicates you need 3 components, they're really not coalescing. It might just be they're just not, because if they were, they would have eigenvalues that would be greater than you'd expect to get by chance. So my process would be, get rid of the individual items that we need to get rid of by looking at the univariate MSA values and the communalities, and you get rid of some individual items, then determine how many components you should extract, and then look at your final solution to determine what loads or doesn't load on each of those components. But nothing wrong with looking ahead if you feel that there's some evidence there that could be useful when you determine the number of components. There's nothing wrong with having that be a consideration. I just don't know that.
Well, with 3 being close, right?
Yeah, that'd be good. That's a really good point. Yeah.
Close or not close enough.
Yeah, that's a really good point. Yeah, and so you could scroll ahead a little bit and look at the actual solution, and you could see, well, does that 3rd component, does what loads on that? Is it anything meaningful? Oh yeah, it is something meaningful, so I'm going to keep that sort of ridge case, that one that was sort of on the edge of you could go either way with. So I do like that thinking. So yeah, certainly that kind of assessment would be perfectly appropriate.
But if all the, in line with Chris's question, but if all your items are loading on all the components, then how do you sort of?
But they don't all load equally on all the.
So then you would-
So we'll look at some criteria here in a minute for how we should read the final solution. Good. Everybody, north and south, nod your head. Yeah. Okay. You know what I didn't have? I mentioned, who did I talk? I saw Pavitra earlier at the library, and last week I had probably 8 or 9 meetings. This week, guess how many meetings I had?
None.
0. I don't know. I would have thought there would have been, huh? Yeah. So we'll see. But I'll be here during spring break. If you're here during spring break, we can meet. So if this is a little fuzzy, and then you'll have a couple days after you get back from spring break to. Although spring break probably won't make it clearer. So I don't care what you do for spring break. It's probably not going to make it clearer. So getting it done before then probably would be great. So I don't know where that leaves us. Made that change. So after just sort of the narrative with my analysis, after rerunning the principal component analysis that extracted 3 components, 6 variables had to be removed one at a time because of low commonalities. The fact of the matter is either I get rid of these now or I get rid of them later. The parallel analysis and the discrete plot was rerun to help determine the number of components with 9 variables, right? So I had to go back and I had to delete some variables. So my parallel analysis was no longer appropriate because I started it with 15 and now I have 9, so I have to rerun the parallel analysis with 9 variables instead of the 15 variables. Same height, just different width. And then this is the 9 variable solution. And I think we probably have that down. We're not going to, and we don't have the time to sort of go through that step by step. If somebody has questions about how we would use that parallel analysis to do this assessment, we can talk about that after class. And then this is like the final step of the maybe final step is just a bit much, but there's not much to do after this. And so what we need to do is we need to interpret our solution. And what we're going to interpret is these matrices. And if you use Vermax rotation, which I did, we're going to look at the factor pattern matrix, or just pattern matrix. If you did one of the orthogonal rotation methods, direct Obermann is the one that I mentioned. There's a matrix that we're going to interpret that's called the rotated component matrix. So depending on which rotation method you use, you just have to make sure you get to the right matrix. And then we're going to start at the left, which is the first component, and then move to the right as we interpret our components. And component loading criteria, because this is exploratory, it's a matter of preference. Here's a couple criteria that we might use. I would start with the simple criteria, and we're going to examine the matrix loadings for items loading greater than approximately 0.4, absolute 0.4, to make certain that each item loads on one and only one component. And we'll talk about that in just a minute. Items with 2 or more loadings greater than approximately 0.4 are considered cross-loaders. Cross-loaders should be deleted from the analysis and the analysis rerun. We should have to do, you might have to do some of that. Well, we'll have to do less of that because we got rid of a lot of those problems earlier. But in my case, with this analysis, it still didn't solve all the problems. Remember the measure of sampling adequacy was 0.72? And what did it say? We are wretched? No, one better than wretched. We were,
Second rate.
what was it?
Second rate. I believe.
Second rate is what we're and so we have sort of second rate. You're going to see the results here are sort of second rate. They're messy. We have to get rid of a lot of variables, and so if I saw somebody's measures of sampling adequacy and they were in the 0.9 range, you're going to have a much different experience than we have with this data, because this data is not nearly as factorable as your data. And then I give you another criteria, and we'll float back and forth between this page and the next page. But this is the rotated component matrix, and we're going to start on the left with the first component. Remember, I told it I wanted to extract 3 components. Here's our components 1, 2, and 3. Where there's no values here, the reason why there's no values here is because when I ran the analysis, just to make sure you know how you got this, under options, I said suppress small coefficients, absolute value below, and I said 0.1. So where it's just blank, it's because the coefficient is less than absolute 0.1. You could change this to a slightly higher number if you so chose.
This is the rotated component matrix that you've got after you did the payload analysis.
That's right. That's right. Got to a point where I was comfortable with got rid of the items that I needed to get rid of, comfortable with the number of components I was extracting, and then I'm ready to try to understand my results. And so going back to our results, we're going to start at on the left-hand side, the first component. And what was the criteria? 0.4, right? So if we look at how the respondent feels like a respondent feels selfless, caring for others. The syntax there isn't perfect. Only loads on one component, and it loads fairly high, right? Certainly above 0.4, right? This loading here is 0.735, right? And what's the value here? Less than what? 0.1, right? And the value here is less than 0.1. So it's definitely not a crossloader, right? It loads high here, and it loads low on the other 2 components. And then looking at the second question, assisting people in trouble is very important. And what this is telling us is these 2 questions tend to correlate highly together and tend to be uncorrelated with the questions that land on component 2 and component 3. The correlation isn't 0, because it's never going to be exactly 0, but they tend to be uncorrelated. And so assisting people in trouble, are we comfortable with that? Is that a crossloader? Using our criteria. Why not, Tyler?
It is at 0.14, but it is, I guess, but it's so minimal.
Yeah, and what's the criteria that we use?
0.4.
Yeah, so if we go back and look at our criteria, the simple criteria, examine the matrix for items, loadings greater than absolute 0.4 to make certain that each item loads on one and only one component. Items with 2 or more loadings greater than approximately 0.4 are considered cross-loaders. That certainly, in our case, the second question is not a cross-loader using that criteria, right? Greater than 0.4, not even close.
Right.
Not even close, right? So those 2 items look good, and then we're going to look at the third one. And the other preference that I asked for in the options is I asked for to sort these by the size of the coefficient or the loading coefficient, and that's why things sort kind of neatly, because you can see these first 4 questions load on this first component. The 5th through the 5th, 6th, and 7th load on the second component, sort of. And then these last 2 questions seem to load on the third component. So, and if you ask, where I said I wanted to suppress values less than 0.1, there's also one that says to sort the results. And that sorting is what sort of puts this in an order that's more manageable. If you don't do that, you'll still be able to figure it out, but it's just not quite as clean. So,
Is it sorted by size?
what's that?
It says sorted by size, so that's what you want us to click.
Right. It's just sorting by the size of the coefficient in the loading coefficient in each of those in each of those columns. And so if we look at the 4th, we do the third. The 3rd is that is that a cross loader?
No.
No.
How about the 4th?
No.
And so these 4 questions sort of load together, and then if we look at the 5th, is that a cross loader?
No.
Offered a seat to a stranger during the
No.
passport? No, that's good, right? 0.779 and below 0.1 on the other 2 components. Carried a stranger's belongings. Looks good. By the way, minus a negative number. Let's say this was a negative 0.715. It means you need to reverse code. You need to reverse code your data, for sure. In this case, this is negative 0.139. So on this component, it's negative, but it doesn't load on the third component. It loads on the second component, right? If on the component that it loads on, if it's a negative number, just go back and read your question, and you'll see that it's in the opposite direction as all of the other questions. High values mean low of the thing, or low values mean high. There's just no doubt about it. It needs to be reverse coded. The only exception to that is if it's a cross load. If it cross loads, you probably just need to get rid of it from the analysis, and then sort of all bets are out. But if you, let's say this was negative 7.15, I would just go in and recode that variable, and then it just would get rid of the negative sign. It would just be exactly the same value. It would just be 0.715. So does that make sense? So negative numbers on the component that it loads means needs to be recoded unless it's a cross load. Yes, Amanda?
Hold on a second. I wrote that down.
If it's a cross loader, we're gonna delete it anyways.
That's right. That's right. But if it's a cross loader, it won't do you any good to read. You might look at it and see it's negative. I'm going to recode it. But if it's a cross loader, it's just going to be it's still going to be a cross loader.
So if it was for that one, the negative sign, if you reverse coded it, would it change the other 2, like
No.
component 2 to a
It
negative?
won't.
Okay.
It will only change that. If that was a negative, in a different reality, if that was a negative 7.15, and we reverse coded that, it would be a positive 0.715. Everything else would stay exactly the same.
What I understand, like what I'm supposed to be looking for, but what it actually means, what component loading means, I'm a little unclear.
Okay, good. I think,
Picture, I'm not really getting.
yeah, I think that's a piece of the picture we need to fill in a little bit. So
Okay.
my guess is others are equally unclear, and hopefully in the remaining, we have whole 10 minutes left. Is that what it is? Yeah. 11 minutes left. We have plenty of time. We'll be able to clarify that. So looking at the rest of well, let me ask, does everybody understand what component each of these questions are loading on? That part is fairly, so if we look at this is good, that's good. Is this good? Has given money to a homeless
Yes.
person? Using the simple criteria, yeah, it meets that criteria. And then if we look at giving money to charity, is that a cross-loader? And volunteer work for charity, cross-loader?
After his, the second to last one, R is giving money to a charity after we reverse code it, because one of them is negative.
No, remember that you only reverse code it if it's negative on the component that it loads on. And that loads on the third component.
So where it's above four.
So I don't have, I wish I should reverse code one of these, just so next time we'll actually have one. That's a real example, because you'd only do it if it's on the component that it loads on. So, in our case, so far, so good. We still haven't sort of taken this to the next step, and the next step really is if we look at these 4 questions that load on component number 1, this is the part where it's as much art as it is science. What do these 4 questions represent? Do these 4 questions represent some dimension of altruism?
Othering behavior.
What's that?
It's like an othering behavior, like towards others, like your attitude.
But the other one said offer seat to a stranger.
Attitudes or values about assistance, helping assist others.
In all of them.
So it's more like internal.
Abstract,
Yeah. These are, and I don't remember what I say, but I take some stab in the dark. These are almost attitudes, aren't they?
Yes.
These are behaviors, right? This is giving a seat to a stranger is actually a behavior. That's something you have to do. Carrying somebody's stuff for them is a behavior, right? Has given food or money to a homeless person, that's a behavior, right? So I would say that the first, and this is, you could say something completely different, and you might be more right than I am. I would say the first 4, we might just call these altruistic attitudes. I don't like the ring of that, but we could come up with something that there's some alliteration there that we could probably build on. The third, or the 5th, 6th, and 7th would be behavioral, right? So altruistic behavior. Again, think about, is there a better way to, it seems a little bit out of the box, we can maybe come up with a better descriptor for that this is where you can maybe use some of your creative powers and creative energy to name it something that has some pizzazz. Don't be sort of institutional and name it something that is just dry and then how about the last 2? What do they represent? R is giving money to a charity. R is done volunteer. Charity, for sure. They're the only 2 that has a charity in the word.
Mm-hmm.
Yeah, and so that might be potentially a third dimension of altruism is I don't know what, something, it'd have to have really charitable, right? And so one of the things that you can do to help you name the components is look at the question that loads highest, because that's the one that's has the strongest correlation with that component. And so by looking at that question that has the strongest loading, that might point you in the direction. But what you really need to do is you need to look more holistically at all of those items that load on each of your components. So we need to look more holistically at all 4 of these, but I might focus my energy on the first one because I know that that's the strongest loaded. Likewise, for the second component, it's 5, 6, and 7, right? I would focus on, well, what is this first one? Well, that's a behavior, and then of course we see that the other 2 fall in line as well. So that's the sort of at the end of the day, that's what we want to get to. And so Amanda, that's the part that matters in terms of what loads on what component is being able to identify and attaching a name to it. And McCroskey, when he did his exploratory factor analysis, if that's what he did, he came up with those names for those. How many dimensions, William?
4.
4 dimensions. What are they again?
Group, meeting, public, and dyad.
Forms of communication and apprehension. he did something similar to this, and he looked at those loadings and he gave those things names, and those names have been with us since the mid '80s or if not earlier. So, so far so good. Yeah, so far so good. We don't have too much further to go. Just a couple other pieces. So if you have a single item on a component, you really just need to delete the variable and rerun the analysis. And so we
like
don't,
number one,
huh?
so like the first one, it only had one, or it only loaded on one, is that what you mean?
No, if we had, this first component has 4 items,
Oh, if it just had.
this one has 3 items, this one has 2 items.
Okay, I see.
If one of your components only has a single item on it, you should just delete that item and rerun your analysis. Because single items probably
In addition,
aren't. What's
is
that?
that where you're looking for anything under 0.5?
Yeah,
Said
you would,
throw out that item if it's under 0.5. I mean,
2 things, yeah. So first, in our case, did we have, because you're talking about cross loaders, right?
I believe so.
We didn't have any cross loaders here, right? What would be an example of a cross loader? Somebody give,
Like that, giving food or money is 0.623, so like that 0.352 was higher and above the.
so let's say this was
0.40.
0.623 and this was 0.7.
Right.
Well, let's say this was 0.623 and this was 0.6.
Mm-hmm.
So then we're
That's a,
falling under 2 categories and then
Above
Yeah.
0.4.
we call that a
I
cross
guess,
loader.
okay.
It's loading on 2 components. We're going to delete that item from the analysis.
Sorry, that wasn't what I meant. I get that. I meant the communalities where it says like initial 1 and then the extraction.
Yeah,
Anything under 0.5
yeah,
to remove and then rerun it.
yeah.
Is that still something we do?
You did that. You did that
Before
way
this.
before you got to this point,
before
right?
this. Okay, but for the homework, we need to do that.
Absolutely. You need to
Okay.
do. You're going to start and work through all of those steps that we work through. Yes.
Okay.
Other. Yep.
You said it's problematic if one of the components had just one item. So like in our case, let's say the component 3 had only 1 item. And since when we were doing the parallel analysis, the random score was a little bit higher, was tad bit at the 1,000th level. So should we delete the component instead of the item and load it on 2 components? Just in
Yeah.
this
You
scenario?
could. You'd have to do both of them in that case.
Oh, delete it and.
You'd have to change the number of components because if it was all by itself, you'd have to change the number of components to 2 or 1 less than what you had.
Okay, so we could do first, change the component and delete it both at the same time?
You should do them both at the same time in that situation. If you had to set that would only be a consideration if you set the number of components to extract to something other than eigenvalues greater than 1. You set it to 3 or 4. But in some cases, eigenvalues greater than 1 is also going to be what the parallel analysis tells you to do, so you wouldn't have to make that adjustment
And
in
the
that case.
parallel analysis syntax you'll post to.
I'm going to post that to Canvas as soon as I get a chance, by sometime this evening,
Okay,
for
no
sure.
rush.
All right,
We'll get to it.
and then single item components, 2 item components aren't much better, and generally they're frowned upon. But if your 2 items are highly correlated with each other, say above 0.7, there might be some good justification for keeping that. If it's not, you probably need to delete the 2 item component and then readjust your analysis to include changing the number of components if you need to change the number of components.
So like on the slide before, it was 0.8 and 0.7. Is that what they were? Yes. Like on the part,
Yeah.
those highly correlated.
These aren't, but this isn't the correlation. This isn't the correlation between the 2 items.
Oh, okay.
This is the correlation with the item with the component.
Okay.
So it's a different correlation
Okay.
this does really represent the correlation of the item to the component, not this item with this item.
Oh.
And what this is saying is that for 2-item components, we just need to look at the correlation between the 2 items. And if it's less than 0.7, it's probably not reliable. And we probably should remove the variable. And so I went through, and there's a couple other slides that you can take a look at. One of the things, so I did the correlations. My correlation between those 2 items was 0.381, certainly less than 0.7. I probably would delete those. They don't seem, there's no, we can't use normal reliability measures for 2-item components. We have to use correlation. And so it's just not a reliable measure. I reran the analysis again. Here is the results that I get after running it again. Looks very similar to what we had before, just that I don't have that 3rd component with the 2-item. And this is just a little bit of language about selecting this is just a little bit of language about what do you do once you're done with your analysis. And this really isn't necessary for the homework for the week after spring break. And this certainly isn't necessary, but we'll continue this conversation when we get back after spring break, after I talk about the nonlinear analysis of the income and education. I have to make myself a note or I'm going to forget. That's 2 weeks away. Then we'll pick back up here, but this really isn't needed in order to get the homework number 4 done. So questions about homework number 4? I will see you on the 22nd, if not before. Have a good spring break.